Remember when your geometry teacher told you that triangles were some of the most important figures in geometry? And then you had to go and solve proofs? Well, they weren't completely wrong. Triangles, and more specifically trusses, are the building blocks of modern infrastructure. The base shape of a truss is three members connected to form a triangle linked with pivot points. The reason a triangle is used is because it is the most stable structure. Tension and compression. Members of a truss can either be in tension or compression. When they are in tension, force is exerted outwards and the member is being stretched. When members are in compression, force is applied inward and members are being compressed. In order to design, analyze, and ensure the safety of trusses, the force that the truss can bear must be determined. Let's take a look at an example of how we can do this. In this example, a truss is supported by two pillars and an applied force of 50 newtons is present. We first begin by drawing a free body diagram. Because the truss is not moving, we assume that the truss is in equilibrium. This allows us to be able to write our equilibrium equations. The net force in the vertical and horizontal directions must be equal to 0. We can deduct from this that F sub A horizontal is going to be equal to 0, as it is the only horizontal force acting on the system. Furthermore, we can write our equation F sub A plus F sub E minus 50 is equal to 0. The reason why the applied force is negative is because it is pointing in opposite directions as the two pillars pointing upwards. But now to determine the force in each, we can use our torque equation. Recall that our truss is in rotational equilibrium as it is not rotating. This means that the next external torque is equal to 0. The torque is defined as the distance times the force. Because our two pillars are located at the same distance from our chosen pivot point, they will exert the same force on the truss, which is going to be 25 newtons. The main takeaway is that trusses are everywhere. They are in roofs, they are in antenna towers, which is how you're watching this video, they are in bridges, and even in some of the world's most famous monuments, like the Eiffel Tower. Allow engineers to build bigger, larger structures that are stronger and can hold more weight. Furthermore, it is a great cost-effective product as it requires little materials. Next time you're driving around, make sure you look around for trusses because they're everywhere.